So what's the first thing I need to do? All right, I think I heard free body diagram. That's a good place to start. So let's draw a few free body diagrams. I'm going to need 3 of them because there's 3 objects of interest. We'll do the first one on mass 1. All right, mass 1, how many forces are acting on mass 1? 2 forces. I've got tension pulling mass 1 up. I've got gravity pulling mass 1 down. Good. Let's just do the free body diagrams. We'll do all 3 of them. So on mass 2, how many forces are acting on mass 2? What are the 3? That's F sub n and tension. Very good. And then I'm going to do the ball over here, I guess. All right, how many forces are acting on the ball? There are 2. There is tension, and I'm going to call this tension 2 because it's different than the tension in this rope. And then there's gravity. I'm sorry? There is no surface, so there's no normal force, correct. All right, those are my free body diagrams. All right, make sure you can draw these without me helping you. All right, that's the first step to success on an exam involving Newton's laws. All right, and make sure that's clear. Don't invent forces like normal forces acting on balls that don't have surfaces like Sean pointed out. All right, so once we draw the free body diagrams, the next thing we need to do is apply Newton's laws. So I'm going to start with mass 1. This is going to take up all sorts of space. Start with mass 1. I've got the free body diagram, so it's, a lot of my work is done. So I need to sum the forces in the y direction. I'm going to use my typical up is positive y, right is positive x coordinate system. So tension is pointing up. I'm going to subtract off the force due to gravity. Those are the only 2 forces. That's the net force. Newton's second law says if I add up all the forces, that's going to be equal to the mass times the acceleration of the object. All right? I can write this as acceleration 1. Let's do that. Let's do that for now. All right? If I look at mass 2, I need to apply the same Newton's law, except this time it's going to be in the x direction, so sum of the forces in the x direction. If I add up all the forces, looking at my free body diagram, in the x direction I just have tension. And that's equal to, again, now mass 2 times the acceleration of object 2. All right? I don't need the y direction for mass 2 because it's accelerating in the x direction. The y direction does tell me that the normal force is equal to gravity, and that's about it. But I don't need it for this problem. All right, here's the problem, though, is I have one unknown. I don't know this guy, I don't know this guy, I don't know this guy. I'm sorry, I don't know tension, I don't know A1 and A2. Right now, I have 3 unknowns with 2 equations. So I need another equation. Now, maybe some of you have looked at this like we did in the problem example yesterday and said, okay, well, I know something about A1 and A2. They're equal. The magnitudes of A1 and A2 are equal. So I can write down that A1 equals A2. I'm just going to call that A. Because they're attached by this cord. All right? If this one moves downward, this one's going to get pulled to the right. The cord can't stretch. That's one of our assumptions about cords and ropes in this class, which means that the accelerations have to be equal. So for all intents and purposes, this is just one object. All right? So A1 equals A2 equals A. The only thing I have to worry about, so the first thing I can do here is I can erase my subscripts. Yank that off. But just like in our example yesterday, I have to be careful about the directions. Remember, this thing has to be sort of a vector. So I've got to have a positive or negative sign if the mass is accelerating in the positive or negative direction. So for mass 1, this is going to accelerate downwards. And I said that up is positive, so I need to make sure that I have a negative sign there. If I don't do that, I will get the magnitude of the acceleration wrong. All right? Mass 2 is going to accelerate to the right. That's the positive direction, so I'm safe here. All right. Does everybody get that step? If you were tasked to do a more complicated problem, which you probably won't be, this is a key step that people miss when dealing with pulley problems like this. If we have like 5 objects, you have to be able to relate the accelerations with all 5 objects. Yeah?
So let's say there was like 8 of those pulleys, as long as it was attached by the exact same thing, all of the accelerations are going to be the same?
They would all be the same. They might be up, down, left, right, so you might have negative signs being different, but they'd all be the same magnitude.
It's attached to the same.
Exactly.
Okay.
Yep, because our chords don't stretch. If they stretched, you can imagine mass 1 moving down, and then the rope stretches, and mass 2 just sits there for a while. So that makes it a lot more complicated. All right, so now I have 2 equations for 2 unknowns, and I can solve this. I have an equation for tension right here. I might as well just plug this guy in. So I'm gonna plug this equation in right there. And what I will get is an equation, I'll just call it number 3 to give it a little bit of its own designation. So I'm going to have tension, which is m2 times acceleration, minus the force due to gravity. That's on object 1, so I should subscript that with 1. So that's mass 1 times g is equal to negative mass 1 times acceleration. All right, so all I did was plug this equation in here and then evaluate the force due to gravity on number 1. I just need to do some algebra, so I'm gonna bring like terms, the a terms onto one side. So we will do m2 times a plus m1 times a is equal to m1 times g. If I factor out a, I get a times m2 plus m1 is equal to m1 times g. And then I can solve for acceleration, which is just m1 times g divided by the total m2 plus m1. I look at this and I'm fairly certain that's right. Why? Why do I look at this and think that this is okay? Yeah, Derek?
Well, because it's leading as one object, so it's dividing the force of gravity that's pulling the whole system by the total mass of the object.
Okay, so yeah, you're sort of, if you treat it as one object, you could sort of imagine that we'd have to divide by the total mass. The other reason, similarly related to what you just said, is that if I don't expect it to fall at g, it's got to be slower than g. And I know that m1 divided by m2 plus m1 is less than 1, right? Because the total mass of both objects is less than one of the individual masses. So I'm multiplying g by some factor that's less than 1. So I know it's less than g. So that's good. That's an easy check. Make sure you're not accelerating faster than gravity. That would be bad. So if I solve that, who's got a calculator on them?
1.53 meters.
You said 1.53? That sounds good to me. So acceleration, if you plug in the masses, you get 1.53 meters per second squared. All right, so that's our acceleration, but what we're after is not the acceleration. We're after this angle, theta. So in order to get theta, let's see if I can do this. I need to look at this. Actually, all I want to do is this. Going, stop. All right, I want to look at this guy. Make it go. All right, so now I want to go to my third free body diagram. Okay, so the one thing I have to draw here is the axis that I was dealing with. The angle theta, that's this angle. Remember, it was from the horizontal, right? It was from the horizontal? Yes, just making sure. From the horizontal is theta. All right, so I know that in order to find anything to figure out theta, I'm going to have to break up tension into its components, T2 into its x and y components. So let's do that in, I don't know, green. So here's the x component of tension, and there's the y component of tension. So this is T2x, this is T2y. And then once I do that, I just need to apply Newton's second law again. All right, so rinse and repeat, just like we've been doing all along. So if I apply Newton's second law, let's pick the x direction. Some of the forces in the x direction. Why would I pick the x direction? I hear it. The acceleration is in the x direction. Okay, it's accelerating in the x direction, and I know the acceleration now. That's why. All right, this is a tricky setup. You know, looking at our original picture, it actually is not obvious that this is going to accelerate in the x direction. Some people like to think it's going to accelerate up along the rope here. Because you're just looking at it and you're sort of thinking, oh, the rope's pulling it that way, so it's going to accelerate that way. No, no, no. Once this thing gets back here to where it's at this fixed angle, it's going to accelerate to the right. Okay? It's not swinging, okay? It's not swinging at all because it's accelerating. The whole thing is accelerating. If it's stopped, if the mass has stopped accelerating for some reason, then it would start to swing, right? Because now it's a different sort of motion. Something else is going on.
So position will go in the y, but not acceleration.
So no, the position won't change in the y direction either, because it's only accelerating in the x direction. So once it starts moving, once it starts accelerating, it's going to be at this fixed angle relative to the vertical as I've drawn it. And it's basically, if you follow along, if you move with the object, it doesn't look like the ball is moving at all. Right? If you accelerate with it, it's only accelerating in the x direction. It's only moving in the x direction until you somehow stop it. Then it'll swing all kind of funny and it'll move wherever.
So it's start like this, though, like doing that. In the y.
Yeah, right. So initially the ball's hanging, and then you push it. Then it'll resist motion. So you know it'll go like this, and then it'll be dragged along like that. Okay. Yeah. So we're sort of looking at it after it starts to accelerate from that point forward. All right. So here's our picture of some of the forces in the x direction. Well, I can write down those. It looks like it's going to be T2 to the right, T2x to the right. That's it. I just have one force pulling it to the right. All right, that force is equal to the mass of the ball times the acceleration. Okay? So I know the acceleration. I don't know tension. I don't know mass. All right, so that's a little bit weird. So let's say, what happens if we actually do summation of the forces in the y then? So in the y direction, I have T2 in the y direction minus the force due to gravity. It's not accelerating in the y direction, so I have 0. So what this says is T2y is equal to mass of the ball times gravity. All right? So I still have a problem here. I don't know this guy, I don't know mass, I don't know this guy. So what I need to do then is, just like we've been doing all along, is make T2x and T2y a single unknown. All right, so what I can do then is take a look at T2y, and I can say that, well, that's actually equal to the tension times the cosine. So this is T2y, that's the angle adjacent. So T times cosine theta, it's equal to the mass of the ball times gravity. All right, so then I can solve for tension. It's equal to the mass of the ball times gravity divided by cosine of theta. This equation up here I need to write in terms of just my tension, which is now it's going to be T times the sine of theta is equal to the mass of the ball times the acceleration. And I can take this and plug it in up there. So what I get then is mass of the ball times gravity times the sine of theta divided by the cosine of theta. All right, that's just plugging in tension up here, is equal to the mass of the ball times A. All right. Thank God, mass of the ball on the right cancels out with mass of the ball on the left. And now I'm just left with my single unknown theta. So sine of theta divided by cosine of theta, that's just tangent of theta. If I move gravity to the other side, I get sine of theta, or tangent of theta is equal to the acceleration divided by gravity. I'll just solve for acceleration. I know gravity is just 9.8, so who can tell me what theta is? The inverse tangent of 1.53 divided by 9.8. 8.87? Okay, so that's our angle, 8.87 degrees. All right, so we started out in the x direction with the ball because we know it's accelerating in the x direction. It turned out that, yeah, we did need to do the y direction in this case, just because we didn't have quite enough information. But at least at least having thought about the fact that it's accelerating in the x direction, we wouldn't have done extra work had we not needed to figure out what this tension term was.